Hello again. I wanted to make this second video because of something I experienced about 6 weeks ago when I gave my pre-calc final exam to my freshman college class. All the problems on that test that stumped them, it was proving or verifying trigonometric identities that really threw a lot of my students. I'd say out of 24 kids, maybe 6 got those right. The rest either got them wrong, or in many cases, they didn't even attempt it. This is after we went over it in class, but that was with the traditional Western way. The Vedic methods trivialize all this. What they do is in American football we call it an end run. We go around the defensive position instead of going through it. What Vedic math does is they take all the trig identities and make them into x and y variable equivalents, thereby bypassing the need to see what are the relationships between all these trig functions. When you put them into the actual identity problem, you end up only having to solve the identities of the variables to prove the left side of the equation equals the right side, and you've bypassed a huge problem. I'm just talking about this now. I want you to actually see it. So we're going first after this shot of me is over. We're going to just go over the identities we have to understand first, and then how to conquer them. Okay, here in part 2, we're going to deal with the reciprocal and the Pythagorean formulas of trig. This will be essential to solving and proving identities. So let's get started. These are pretty basic. I'm not going to lie, it's not that hard to memorize, especially the left side, which is much more common than the right. But I'm mentioning it anyway because in Vedic math, by simply substituting y's and x's into this, they make whatever identities you have to prove so much easier. So for instance, secant x would be 1 over cosine, which would be basically 1 over x, because the cosine is the x coordinate and the sine is the y coordinate in the so-called unit circle, which we'll go into briefly. All right, Pythagorean identities. This is the big one. Everyone should know this one. These are the variants when you transpose and want to isolate one of the variables. So it's pretty much common sense. This is also derived from unit circle thinking. These two are the scary ones because a lot of students just don't know a way to memorize it. There is a way to memorize it. You can just derive it by dividing the basic sine and cosine squared on top by either cosine all through or sine all through, which we'll go into. So these do come up. In Vedic math, this is totally avoided. Everything is going to be x's and y's. You don't have to worry about knowing this once you put the initial identities into x's and y's. So let's go into the last one. Here's what Vedic does. They basically take the unit circle, if you remember that. I'm not going to redo it. We have to save time. If you remember, in the unit circle, the hypotenuse is going to be a radius of 1. So the cosine will just be an x coordinate because you're basically saying base over hypotenuse is x over 1. That's x. Likewise, sine would be y over 1. That would just be y. The secant is just cosine reciprocal, cosecant sine reciprocal. See how simple this is when you make it into variables? Vedic also takes the basic Pythagorean theorem of the unit circle and just makes it the variables. And likewise, transposing and isolating. And those scary ones about 1 plus tan squared equals secant squared, or 1 plus cosine squared equals cosecant squared. That never seems to get to that point. The x's and y's always seem to work themselves out, so you don't have to memorize all this stuff. So this is a very brief introduction, and we're going to get started with the nitty-gritty right now. Okay, I'm about to present to you some typical identity verification problems. I'm going to do it in 3 progressive levels of complexity, i.e. 3 problems. And we're going to compare the Western with the Vedic. Okay, our first problem is going to be fairly basic, no really fancy identities. But we're just going to see how a Western person might solve this. So we're going to start right away. We'll do the left-hand side and see what happens. So the numerator is going to be 1 over cosine squared t. It's the reciprocal. And the tan, you should know from basic trig, will be sine t over a cosine t. Now, one way to simplify this is we could maybe just, since we're dividing by this fraction, we could invert and multiply. So I'll write the numerator again, times cosine t over sine t. We could cancel these guys out. We'll have a cosine t in the bottom. You'll have 1 over the entire denominator. And then we can finally say, oh yeah, I know. If 1 over cosine is secant and 1 over sine is cosecant, then that indeed does equal secant t cosecant t. A pretty straightforward way. This is the Western way. Not too difficult. Watch what the Vedic does now. So with the Vedic method, secant squared t will be 1 over x squared. The reciprocal for cosine. And tan will be y over x. Once again, we're going to invert and multiply. X over y. Cancel. And we have, basically, let me put an x there. And you're already finished. Already finished. Okay? There's your 1 over x, 1 over y. If you want to write it down as secant, cosecant, fine. But see how... And notice, and not only was the Vedic faster, even though there was no special identity you had to really memorize, it was still so much simpler, cleaner, and faster. Okay, we're going to extend the level of difficulty a little bit more now. Look at this equation. We're going to say 1 over 1 plus sine theta plus 1 over 1 minus sine theta equals 2 plus 2 tan squared theta. And you might think, what are we going to do now? So a typical Western approach might be, we're going to deal with the left-hand side only first, trying to make it more presentable. We could cross multiply and then have a lowest common denominator on the bottom. So if we cross multiply, we'll have a numerator like this, 1 minus sine theta times 1 going up to the left, and then 1 plus sine theta times 1 going up to the right. Okay? And that numerator would simplify, the signs cancel out, and we just have 2 in the numerator. Now in the denominator, it's going to be one of those a plus b times a minus b cases where you have the result a squared minus b squared. So it's going to simply be 1 minus sine squared theta. Now you would have to know the Pythagorean identity, sine squared plus cosine squared equals 1, and the variant 1 minus sine squared theta equals cosine squared theta. So we could just put that over here, because basically one equals the other. And now that's the left-hand side, but let's simplify it a little more. Okay, since cosine is the reciprocal of secant, we could also say 2 secant squared theta. That is the left-hand side. We are now going to deal with the right-hand side. So we see we have a common factor of 2. So we can say 2 times 1 plus tan squared theta. But guess what? Remember one of the Pythagorean identities? This equals secant squared theta. So that's our right-hand side. And we got the equivalence right there. Left-hand side and right-hand side are equal. In order to get this thing right, you had to know the Pythagorean variants. One variant here and another variant here. That is the typical Western way to do it. Now we're going to go to the Vedic. So for the left hand, we can say 1 over 1 plus y plus 1 over 1 minus y equals 2 plus 2y squared over x squared. Okay, so what could we do next? Well, one thing we could do is perhaps we can do the same thing as before. We can cross multiply. We can do 1 plus y plus 1 minus y over, and we again we have that a squared minus b squared, 1 minus y squared. Okay? And that's going to be, well, I better write down left-hand side here just to make sure you understand. And we have 2 again over 1 minus y squared, which you should know is x squared. Okay? So we go to the right now. Watch this. The right-hand side is going to be 2 times 1 plus y squared over x squared. Now, without doing any trig identity, what we could do is make this x squared over x squared. So I want a common denominator here of x squared. So I could basically do this. 2 x squared over x squared plus y squared over x squared. Now watch what's happening here. X squared plus y squared equals 1. So it's going to be 2 times 1 over x squared, which is 2 over x squared. And lo and behold, we had 2 over x squared on the left and 2 over x squared on the right. We didn't have to memorize that 1 plus tan squared equals secant squared, which would have complicated things. So there is some algebraic manipulation. I'm not going to lie to you. But notice you don't have to memorize these strange identities that you're forced to memorize in high school. So I'll call this level 2 of complexity. We're going to go to level 3 before we start. We now come to our pièce de résistance. We have a pretty complex looking trigonometric equation. We have to try to verify this. Now, if you're not sure what you're doing, you're going to be bogged down in endless sine and cosine permutations and combinations to try to solve this. Those who have some familiarity with Western trigonometry will know we see some basic identities here. Of course, you've got to know them. So I'm going to write them in little by little so you see what this really is. So the entire first fraction is the law of tan of a plus b. The numerator of the right-hand side is the law sine of a plus b. And the denominator of the right-hand side is the cosine of a plus b. So once we have these laws in place, it gets more obvious. We know that tan is sine over a cosine. So we basically already solved the problem. So here it is. I deliberately picked this problem for a reason. I wanted to show the Western method at its very best, i.e., you know the identities, you see it right away, and you solved it in only a few seconds. So you'd think, how can Vedic math improve on this? Well, Vedic beats it for a very simple reason. You don't have to memorize any of the identities, and you can still prove it. So we're going to go to the Vedic method right now. Vedic math is very smart. It doesn't even deal with the trig functions at all in the beginning. It deals with the variables only and sets them up. We have 2 angles here, so we're going to set up a triple, which we're really not going to be using for this problem, but the triple will be illustrative of something. I'm going to make angle A the triple x1 for cosine A, y1 for sine A. R1 is going to be the hypotenuse, which you really don't need, but I want to show you for illustrative purposes of what a triple looks like. Angle 2, or angle B, excuse me, will be x2, y2, cosine, sine respectively, and r2. And we're going to be dealing with the x1s, y1s, x2s, and y2s extensively. We're going to be putting them in these expressions, and we're going to see how it works out so beautifully without having to worry about any of these identities. So dealing with the left-hand side, we're going to take the numerator, tan A, as y1 over x1, plus tan B, y2 over x2. That entire thing over 1 minus tan A, tan B. So let's put this in first. That's the left-hand side. Now for the right-hand side. So sine A is simply going to be y1. Cosine B is x2. Plus cosine A is x1. And sine B is y2. We go to the bottom. Cosine A is x1. Cosine B x2 minus sine A y1, sine B y2. And that's our basic Vedic setup. And we're going to work from this. We're going to deal with the left-hand side and simplify it by taking the common denominator of the whole denominator and using it to greatly clear up and simplify this entire expression. So we're going to call this, I guess I can call it lowest common denominator. I'll call it LCD, lowest common denominator. That would be x1, x2. Right over here. We're going to multiply everything by x1, x2 on the top and x1, x2 on the bottom. So I'm going to move everything to the right a little bit to make room for that. I'll leave out the right-hand side for a while. I want you to see what's going on with the left-hand side first. So let's multiply the common denominator by the numerator first. So if you notice, the x1 cancels out. So we have our first term as y1 x2 plus the x2 cancels out. So we have y2 x1 over. Well, this 1 simply becomes x1 x2 minus, and notice the entire x1 x2 cancels out. So all we have left is y1 y2. Now you may not know it, but we've already solved the problem. Look at this left-hand side and look at the right-hand side. We have to do a little commutative property here. The y2 would go first here, x1 would go after. This one's the same. We have solved the problem. All we had to do was some algebraic manipulation. We didn't have to identify anything, and Vedic math wins again. So I want to make sure you understand the value of this powerful, powerful weapon. This ends video 2. I hope you enjoyed it. I want to make sure you can internalize this. You may have to see it more than once. This should empower you, and hopefully you can transmit this to your students. And if you are consultants or coaches, to your teachers. I wish you guys good luck, and I greatly enjoy teaching you guys.